In this lecture, let's discuss what a power MOSFET is, how it's constructed, and some of its basic characteristics. So here's a cross-sectional view of a power MOSFET. So if you take a silicon wafer and cut it and look at it from the side, this is what it looks like. Generally, you see something like this. So you have the vertical current flow through the MOSFET and really through just about every power device. So for example, the drain here connects to the bottom of the silicon wafer, and the source and the gate are put on the top side. What we can see here is that the cross-hatched regions represent metal contacts. So we have metal contacts to the drain and to the source. This shaded area here around the gate is the oxide layer of silicon dioxide or glass that insulates the gate from the rest of the MOSFETs. The clear area inside that is the gate. That is usually a polysilicon material, but it's a conductor that forms the gate. And then we have the doped silicon. This is an N-channel MOSFET. The source is connected right here. The drain comes from the bottom at this N region where there's slightly doped material, and the drain is actually right there. So we have a MOSFET that connects to the drain and source like that. The P material is called the substrate, and in a practical power MOSFET, that substrate is shorted to the source. This particular structure shown here is called the DMOS structure, in which the gate and the source are built laterally on the top surface of the MOSFET. We also have other variants, grooved structures such as VMOS or UMOS, or sometimes known as by trade names such as trench MOS, are devices where grooves are cut into the top of the side of the silicon, and the gate is actually built vertically along the side of the groove. We also have the super MOS structure, which is a relatively recent improvement that reduces the on resistance of high voltage devices. And so we have some very good 600 volt MOSFET built with the super MOS structure. The power MOSFET is a highly interdigitated device, meaning that we replicate the MOSFET many times on the top side of a chip and connect all of these little MOSFET in parallel to get one large high current MOSFET. So here you can see there's a channel right here of a MOSFET, there's another one there, there's another one over here, another one over here, and so on. And so we pack these MOSFETs as tightly as we can together to fill the surface of a silicon wafer and build a high current device. So then the current will, when the MOSFET is turned on, the current will flow in the drain, then through the channel and out the source. That's for positive current flow. Actually, a better way to say it perhaps is we have electrons coming in from the source to the N material. They form a gate, is forward biased. They form an inversion layer over the channel that is effectively, it's more N region that connects the source to the drain, and then the electrons flow this way and out the drain. In the off state, where the MOSFET is, the gate is turned off, positive voltage is put on the drain with respect to the source. Then we have a depletion region formed that blocks the voltage, and really this is the same as in the PN diode. And in fact, if you look at the substrate, P material, and this region right here, this actually looks like a PN diode. As we talked about in the previous lectures for the diode, we have lightly doped N region in the drain that gives the device the breakdown voltage that it requires. And so in the reverse state, we have an electric field really across here that has the voltage drop from the drain to source. To obtain a high voltage breakdown rating, as in semiconductor device, we require lightly doped, high resistivity material. In the on state, then again current flows this way, as we've mentioned before. A key distinguishing feature here though is that the current has to flow in this N- region, and much of the on resistance of the device appears across that region. And since it is lightly doped, it has a high resistance, and this is the on resistance primarily of the MOSFET. We do have to put that in series with the resistance of the channel and the resistance of the contacts and the leads in the package, but in general this N- region dominates the on resistance. And in the MOSFET we have a majority carrier device where there are no minority carriers to cause conductivity modulation, the way there is in the diode. So this accounts for why MOSFETs tend to have a relatively high on resistance, especially at high voltage levels. And so a high voltage rated device will have to have a special high resistance N- region, and the on resistance goes up quickly with voltage. So we have very good MOSFETs at low voltage, but at high voltage we start to prefer minority carrier devices that can give lower forward voltage drops. Okay, the MOSFET has this body diode. The body diode actually comes from this PN junction between the substrate P material and the drain. You can see there is a PN junction there, and it's a real diode. So effectively we have our MOSFET represented by the channel, and it's in parallel with the body diode. So this is a real diode. It has reverse recovery, and it can conduct current if it's forward biased, and that happens if we put plus on the source and minus on the drain. Then this diode can become forward biased, and current can flow this way. The diode can conduct the full rated current of the MOSFET. After all, it is the same device. However, the caveat is that the diode is not necessarily optimized for fast switching speed, and it depends on the diode. Some MOSFETs are designed to have, on purpose, a fast recovery diode, and others are not. Here are the static IV characteristics of the MOSFET. This is drawn in a little different way than you might be used to seeing, and it's drawn to emphasize how to control the MOSFET. So the vertical axis is the drain current, the horizontal axis here is the gate to source voltage, and we have the characteristics or lines of constant drain voltage. So basically, if the gate voltage is below a voltage known as the threshold voltage or VTH, then the MOSFET is off. And the gate driver has to bring the gate voltage, the gate to source voltage, higher than the threshold voltage to turn the MOSFET on. So here, as you can see, as we raise the voltage above the threshold for the first few volts, the MOSFET starts to turn on, and when it's up here, it's maybe 10 or 15 volts, the MOSFET is all the way on. And then we have, for a given drain current, we have a given drain to source voltage. So we generally will operate the MOSFET turned on over here, where we have a low voltage, and in this case the drain to source voltage is approximately proportional to the drain current, and we can approximate this as saying the drain voltage is the drain current multiplied by the on resistance of the MOSFET. In majority carrier devices like this, we typically have a positive temperature coefficient on the on resistance, which means that as the device gets hot, the on resistance goes up. So first of all, this makes it easier to parallel MOSFETs. They don't have this mechanism, this positive feedback mechanism that will make one device hog all the current. On the other hand, the on resistance is highest at high temperature, And when we choose an on resistance, we have to be conscious of that and think about, in the worst case, what is the hottest the MOSFET will run, and when is the on resistance under those conditions. Here's an equivalent circuit of the MOSFET to first order, showing the capacitances. So a MOSFET has capacitance from each terminal to each terminal. And we'll talk about what each of these are one at a time. So first of all, the gate to source capacitance is the ideal capacitor of the MOSFET between the gate terminal and the channel, and it's drawn here with respect to the source. So this is the capacitance across here from gate to channel, and we charge up this gate to source capacitance to put charge in the channel and turn the MOSFET on. In addition to that, you can see that there's an overlap between the gate contact and the drain, and this forms what's called the gate to drain capacitance. We do what we can to make that capacitance small, but in fact charging it up does help put additional charge in the drain region and somewhat reduces the on resistance. Typically, the gate to drain capacitance is small compared to the gate to source capacitance. So it's a lot fewer picofarads of capacitance. However, it has a lot of voltage across it. The gate to source capacitance might get charged up to 10 or 15 volts, whereas the gate to drain capacitance gets charged up basically the full drain voltage. And so, although the capacitance is small, the voltage across it is large, and the amount of charge in this capacitance can be large. In fact, in some devices, it is larger than the charge in the gate to source capacitance. This has some impact on and considerations on how we design the gate driver circuit, and we're going to talk about that in the next few lectures. The third capacitance is the drain to source capacitance across here, and this is basically the capacitance of the body diode. It's really capacitance from here to here, and this is the same capacitance that this PN junction diode would have, and it behaves a lot like a diode capacitance. It's non-linear. We didn't talk about this with respect to the PN junction diode, but it's actually a similar kind of function. Here's a classic formula for a depletion capacitance, and it's a nonlinear device that where the capacitance varies roughly as the inverse square root of the voltage. So as the voltage goes up, the capacitance goes down, the incremental capacitance, and we get this inverse square root formula. Okay, these output capacitances of devices such as the drain to source capacitance of the MOSFET and the junction capacitance of the diode are another mechanism that can lead to switching loss. Basically, these capacitances get charged up with energy when there's voltage on it across them. So for example, when the MOSFET is off, we have VG across here. There's no voltage across the diode junction capacitance, but as far as AC signals are going, the junction capacitance is effectively in parallel with CDS, and the two add together. When we turn the MOSFET on, we short out these capacitances, and any energy stored in them gets dumped into the channel of the MOSFET during the turn-on transition. So if this is a linear capacitance, we can say that this capacitance store energy equal to 1/2 CV squared, where here C is the effective capacitance of these if these were linear capacitances. And VG is the voltage at the input of the converter. So we lose this much energy every time we turn the MOSFET on and short the capacitances out. So this would cause a switching loss that is equal to this energy stored in these capacitances multiplied by the number of times per second that we short out the capacitances, or multiplying it by the switching frequency. So this is another mechanism for switching loss. So for the conclusion, a MOSFET is a majority carrier device that's good news because it has very fast switching speed. We don't have all the time that it takes to remove all of the stored charge that was causing conductivity modulation in the diode. And so MOSFETs can switch much faster, and in a MOSFET that is typical to get switching times of a few tens of nanoseconds, and in low voltage devices even faster. So typical switching frequencies, tens and hundreds of kilohertz, are easy, and we have low voltage computer type power supplies that run in the megahertz of switching frequency range because of the high speed of these devices. The bad news though is that on resistance increases rapidly with the rated voltage because these are majority carrier devices and don't have conductivity modulation. So we have good super junction MOSFETs at 600 volts, but we can't go much higher than that because the on resistance has increased too much to where it's not economical to use the device. They're very easy to drive. We simply switch the gate to source voltage between 0 and 10 or 15 volts depending on the design, and very easy to control then when they're on and off. We also have logic level MOSFETs that are designed to operate with a 5 volt gate voltage instead of 10 or 15. One other thing, these devices generally are loss limited. When we design a power converter, we generally don't select the MOSFET based on the current rating, which is a peak current rating of the device. Instead, usually we select them on the basis of on resistance and conduction loss. So often we will choose a device with a peak current rating much higher than we intend to use, and instead we choose the MOSFET size to get a given low on resistance as needed in our application. So as a result, these are very rugged devices as well that have quite a bit of margin when it comes to current.